Hi everyone, I am Jong Yu again from Wan TV channel on YouTube. Today I'm gonna talk about the second part of the Berquist Sherman, and my focus on today is how can can be suggested to adjust the paid loss development triangle historical. And last time I showed you how Berquist Sherman restate the historical case outstanding because they thought it is not adequate. So today I'm gonna talk about how they did to restate the paid loss development triangle. Yeah, here. So I just try to point out again. Uh, I just adjust the case outstanding historical triangle amount it was before, right? ILDM and PLDM. And after I, restate the case outstanding figure, and right now it is reduced, it's even smaller than the PLDM, right? So accordingly, the IBNR amount was a lot, bigger in ILDM. And right now, it is a lot less than the PLDM as well. This is just some of the case outstanding, which is like each individual case, and IBNR is a bulk reserve. So total is a gain. And right now, I'm gonna move on to how the Berkshire Sherman did restate the paid loss triangle. And start with the starting from accident year 1969 up to 1976 is from the original paper, and this is the unadjusted paid loss development triangle on a cumulative basis. And I can get the age to age factor from there, and I selected here for 78 is volume weighted average, which is a basic chain letter, and I have selected. And in order to restate the paid loss triangle, this is a little bit more complicating. They use, regression, and starting point is, oh, let's look at the closed claim count. It means that out of whatever number of claims occurred for each accident year, I keep track of only the closed claim count. And if I do that, like until the ultimate, and eventually I'm gonna get the total number of closed claims. And I can make a conclusion that all those claims that has been closed, probably they occurred in this specific accident year. But because it is a closed claim count, and I can create the closed claim count development triangle on a cumulative basis. And also, I'm given the reported claim count, which is the sum of closed claim count, that is a cumulative, plus open claim count. But here, like closed claim count is given and reported claim count is given. I just subtract the closed claim count, cumulative closed claim count from the reported claim count, and I end up with open claim count. This is the one that I have already used to restate the case outstanding figure, but here closed claim count and reported claim count is given. And one of the so-called, like diagnostic, let's say statistics or index is just, like for a, I don't know, it's just for reference, and it's one of the diagnostic, picture of it, because, I can diagnose, like it's like a closing speed in the in our entity's claim procedure. So you virtually just, like out of total reported claim, it means what? The by the end of, let's say 1970, December 31st, they're all, whatever amount of claims occurred, it keeps adding the closed claim count plus how much claims are still open, right? If you add those together, I can get the reported claim count. So this one is simply just divide the closed claim count by the reported claim count. So out of total reported claim count, how much proportion of the claims are closed by the end of 1970? And there is, some other like diagnostics as well, but it just, gives an idea how we can make a judgment on, claim closed, like speed or something. Now I'm gonna get back to the subject here, and you can use like closed claim count, but here the author probably think the reported claim count is, like better to estimate the future like number of claims. And I start with the reported claim count, and I can have a age to age factor there, and I selected here simple average. So all the way down to the, I thought, ultimate. And here, using the summary table, I end up with ultimate claim count for each accident years, like this, right? Or we can do it like, like based on the closed claim count. It's like, very comparable to PLDM, ILDM. In this case, we can like, estimate the ultimate claim count based on the, cumulative closed claim count or the plus open claim count, which is a reported claim count. So probably in practice, I would compare those two. Like, like there is a significant difference between PLDM, ILDM. There might be a significant difference between the ultimate claim count based on closed claim count and reported claim count. But here, the author, Berquist Sherman, they just did it, estimate the future claim count based on reported claim count. There is a, like, this is like what? The claim counts development factor. And this is quite new concept for disposal rate. So dispose means like what? On, like on my side, I dispose whatever I'm obliged to pay. I'm obliged to settle down the claims, right? And then the disposal means how much proportion of the total claims which I'm liable to pay out has been settled down, right? And then that should be based on estimated ultimate claim count. And then I get this ratio that divide, I use formula this one, out of total, let's say 9,690 claims so far by the end of, like 1972, how much, how many claims are closed so far? Closed means I settle down claims so claimant or policyholder is happy, right? The accident occurs and I pay out all the liability. That's what it's talking about. And I can get the disposal rate development factor. If time goes by, probably it reaches like what? One, right? Out of total estimate of ultimate claim counts, I settle down everything. So it is called disposal rate. And from disposal rate, I can create adjusted claim, closed claim count. So just ignore all the historical closed claim count. I just calculate again based on estimate of, like ultimate claim counts, and I apply this disposal rate, right? And here I don't I don't choose any like, average or anything. I just use the historical disposal rate against the claim count, and this is I've got adjusted closed claim count, right? So you can do it probably, after you select the whatever the average or volume weighted or, simple like average or something, you can select it and you can use it to create the adjusted close claim count. That's all, you should be very creative. But anyway, here author use just historical disposal rate. So I got the different, adjusted close claim count. We can have a look at how different they are, right? Before adjusting and after adjusting. This is report claim count. And here we go, right? So you can see some of the discrepancy, right? It's not a lot, but you have to like remember that this is like, like number of count instead of loss amount. And this is just the preparation stage. Okay, so you have the original closed claim count and right now adjusted closed claim count. This is just for another additional like, review stuff. So let's say accident year 1969 and you have this is unadjusted, okay? The out of total closed claim count and this is a paid loss amount. For year 1969, is there any like, direct relationship between those two? Obviously, intuitively, there exists a direct relationship. We just want to check it, right? So here, using the actually, like it says, it's like exponential regression in an Excel. There is a, like the dependent variable is the paid claims, paid loss amount, and independent variable is number of closed claim counts. And we just, like regressed against this one. And then what about the fitted one is a new X there. So I use that. And here is the result, right? There's a prediction of like a claim payment amount. And I have done the same for accident year 1970 and 1971. And when you look at R square, like this is very close to 1, right? So it's like, it's almost perfect. It's very linear, even though it is exponential. So I'm happy about it. And that's just a quick check upon what you are doing. You can have now, like confidence. And right now it gets more complicating. The way how they design to restate the, like payment loss amount triangle is like this. They apply the regression on a, total, this half triangle. And I denote X and Y, IJ, and the, lowercase. You can have it. This is unadjusted closed claim count. And this is a paid loss amount. And we have just got the adjusted closed claim count. And this one, I put, like n up there, and it means that this is a new independent variable. So like regression system, I use these two data, independent variable and dependent response variable, to come up with the, like intersection and slope. And for the prediction itself, to restate the, like the pay loss amount, I use this one, or just this closed claim count, as a new independent variable. And then when I restate it, I use, for example, here, oh, there's a circled one. And here, when you look at it, right, look at the formula, oh, maybe I should use this one. When you look at it, this is input 2-point regression, right? These two are independent variable, and these two, pay loss amount, are response variable. And from there, using exponential regression formula, I get the, like intersection and slope, and I apply that to predict this number is new independent variable is adjusted closed claim count. I got this. And also here, like this, right? We move it like a chain action. But unfortunately, when I reach there, I'm gonna keep, like drawing here. I reached at the end of it, right? So next one, how am I gonna do that? This one is like this, right? I can use the same one because I don't have the, like whatever the, like, like shorter than 1 year development. So I want to call it, this is like, in this regression, it's like extrapolation. Okay, I can just, understand it, right? And finally, I got adjusted paid loss development triangle, which is all restated. But at this point, 1976, at the latest, like diagonal, that's the starting point. Okay, that's the same as unadjusted paid loss development triangle. Now I got the new one, right? Using whatever very, complicating procedure, and you need a somehow the creativity to understand it, and, like change whatever. It all depends on your actuarial judgment to come up with. But anyway, I restate the paid loss development triangle, and I select, here on view like paid loss development triangle. I apply the loss development method to come up with the ultimate, right? But here now, I would say this is the part of the, like adjustment or restating the paid loss development triangle. But Berquist Sherman, they didn't stop here. So I'm going to do it very quickly. Let's say out of that, the adjusted paid loss triangle, I get like, age to age factor. This is based on the adjusted one. And using this age to age factor, I also apply the, like a two regression, linear regression or exponential regression upon this age to age factor by different development period. And when I do that, it's like, all different like development period, but this is only one, so we cannot do that. And this one is, like 7, because, all 8 year, but when you talk about age to age factor, it is one reduced. And here is all the regression formula. You can get it very easily using the Excel, like formula. And here, this is what I understand. I put it this way. For example, you do the, let's say, apply the linear regression or the like independent variable like this, all above, all the accident years that you have the historical data, right? So this is the response variable, and this is the independent variable, and you get the intersection and slope, and you apply the 1973 prediction. That's what it does, right? And this one is obviously all the way down to the actual historical age to age factor. Independent variable is accident year, and new independent variable 1975, and you get this age to age factor all the way down. So first one is linear regression, and do the same thing. No, actually against the same age to age factor, right now exponential regression. Okay, so it was like, fill up the down below. What does it mean? It's like, beyond 1976, future age to age factor for each development period, and you just use regression to come up with those things. And it is summarized, let's say, unadjusted paid loss. This is loss development factor that you have selected. And this is the basic chain ladder after you adjust the paid loss development triangle, which is, it doesn't look, like big, but in terms of you, if you apply the paid loss amount, which is going to create a significant difference. And also here, against the adjusted paid loss triangle, use the linear regression or exponential regression. And there is a, like loss development factor. And upon that, how we, have like ultimate the claims development, like, the ultimate numbers, all based on unadjusted and adjusted volume weighted average and linear regression and exponential regression. And you can see all the difference. They're quite close, right? So this is what Berquist Sherman did to restate the, like the pay loss development triangle, and also apply again the regression to come up with the age to age factor and get the, loss development factor finally. And this is what the ultimate paid losses accordingly. And this is another like summary of like based on ultimate and how much is for the, future claim estimate, which is the case outstanding plus IBNR, right? Okay, this is what I can, finish today's video. So this is a little bit more complicating than the case outstanding adjustment. And, like back in 1978, and those two brilliant actuaries, they probably, like used to be the consultants, and they have come up with such a very heavy adjustment. I was so surprised, and like looks like wow, this is like very, I would say, oh, it's not a manipulation, right? Because it shows all the like background work, and they heavily use like regression model, probably, which was not that easy even back then, right? Probably they didn't have the computer, and especially the 2 point regression side, like probably all the actuarial scientists under there, and they have done the work using the calculator, This is like heck of a lot of job probably. And this is what I can tell you how Berquist Sherman did adjustment upon the existing paid loss development triangle. And based on that, they come up with the different number of ultimate paid loss amount. And this is what I've got from the original Berquist Sherman. And next one, and I'm gonna show you how or what the Friedland in the that the textbook that I mentioned about, how she applied this methodology to the like whatever her like data. And I already mentioned it, and she shows us a little bit of like creativity there, or she omits some of the procedure there, but we can see how the actuarial scientist could do in terms of our work, and it should be based on all the like statistical knowledge and some of the like regressions, even though the structure itself is quite different than what we have observed and or what we have done. So this is quite interesting to see, right? So I'm pretty sure you guys are like like probably excited about having a chance to look at it, and I will keep like showing you how the Friedland like apply the Berkeley Shaman like adjustment or restating methodology to her own data in the next video. Thank you very much and see you again.